Okay, so starting with the first chapter, basic probability concepts. So first concept, what is a sample point and what is a sample space? So whenever we do a random experiment, let's say you toss a coin, okay? The outcomes, they're uncertain, right? This is an experiment. Tossing a coin or throwing a die, these are all, for example, if you throw a die or a pair of dice, throw a pair of dice. These are random experiments because you don't know the outcome, right? Tossing a coin, it can give you a head or a tail, heads or a tails, and then throwing a pair of die can give you one of these 6 out. No, it's basically one of the 36 outcomes, right? Because I'm throwing two dice together, so you know the sample space. It can be one of these. So either it's 2 1, 2 2, so on. So there are 36 such possible outcomes of this random experiment. So here you just have 2 outcomes. So if you toss 2 coins, you'll have 4 different outcomes. So each of this outcome, for example, if you take this is a sample point. This here is also a sample point. So one of the outcomes of a random experiment is called a sample point. And the collection of all possible outcomes gives you the sample space. For example, here, this entire thing, if you collect all the possible outcomes in a set, that set is called a sample space. So sample point is one of the outcomes, and then sample space is the collection of all possible outcomes. Clear?
Yes, sir.
Next topic here is mutually exclusive events. Mutually exclusive. What does that mean? So here they're not talking about events. We'll go to events later. For now, let's only talk about outcomes. So outcomes is this thing. The sample point is the outcome. So what are mutually exclusive outcomes? Any 2 outcomes which cannot occur together, that is called mutually exclusive. For example, if head comes up, then tails cannot show up at the same time, right? So that is mutually exclusive. And what are exhaustive? So this is something, outcomes that cannot occur together. This is called mutually exclusive. And then you have exhaustive. So exhaustive outcomes is the collection of all the outcomes such that when you collect all of them, you will get the entire sample space. So all possible outcomes. So for example, if you collect heads and tails for this tossing of one coin, then these 2 are the exhaustive outcomes because they make up the entire sample space. And if you only consider, let's say, when you throw one die, it's complicated. If you throw one die, then these are the possible sample points, and this is your entire sample space. So what are the exhaustive outcomes? 1, 2, getting a 1, getting a 2, up to 6. These all 6 different outcomes make it exhaustive because that is the only thing that is possible, and these all outcomes, they complete the sample space. So outcomes that complete the sample space, that is called exhaustive outcomes.
Sir, exhaustive outcomes can be mutually exclusive as well, right?
Yes.
And mutually exclusive can be exhaustive because outcomes.
Yes.
Okay.
Can be, like, it's not necessary in any of these cases.
Okay.
Okay, moving ahead, what is an event? Event is basically a collection of outcomes. How? How is it a collection of outcomes? So, for example, when you throw one die, then if I tell you that getting an even number, that is an event. Getting an even number on the throw of a die, that is an event. Similarly, if I tell you getting an odd number, that would be another event. Because it's, what is that? It's a collection of outcomes. Because getting an even number, you can collect these three outcomes here. Getting a 2, 4, and 6 all will qualify under this even number category, right? Similarly, if you want to only record the odd numbers, all these three different outcomes will qualify under this particular event of getting an odd number. So event is nothing but a collection of sample points or a collection of outcomes. Okay. When do we say that event, let's say event A, I'm just naming an event. We say that event A has occurred when the outcome is one of the sample points that's in A. So, for example, when you throw a die, then if this was event A and this was event B, then if you get a 3 when you throw a die, then you will say that event B has occurred. That's how we say it in statistics. Event A has occurred or event B has occurred. So when you get a 6, then it's event A occurring. Okay. It's just a terminology. When do we say that an event has occurred? So basically, event will be said to be occurred whenever you get a sample point which satisfies one of the means, which is from the space of that particular event. So this is the partition of the space, right? This entire sample space, it's broken down into different sets. So if your outcome is contained in the particular set of the event, then you say that the event has occurred. Next topic here is union of events. Union is basically if you have two events, let's say A and another event is B, then union means A or B, either A or B. So notationally, I'll not write A and B here because A and B signifies something else. I'll not write this. So either A happens or B happens. Then we say that A union B has happened. So union of events is shown as this: A union, and then you have a B. So this is the sign of union. So either A has occurred or B has occurred. That is what it means. So formula wise, there is a formula which you don't need to be introduced right now, but either A has occurred or B has occurred or both, anything. So that will consist of union of events. So if you think about it in a set format, then let's say this is a set of event A, and then there is this set of event B. Then A union B is the entire area that you see here, this entire thing. The full area that is within this set A and B, that is called A union B. Is that okay? So because if you're here, you're in A, that means A union B is satisfied. If you're, let's say, I'll show this here. So if you're in this area, then you're in event A, that means A union B is satisfied. If you're here, that means you're in the common part of A and B, then also it's satisfied. This is the region where A and B both are happening, and here only B is happening. So in any of these three regions, A union B is satisfied. Next is intersection. Intersection of events. intersection is only those where A and B both happen, not only A and not only B. A and B. So if you look at it diagrammatically, only that portion where A and B both happen together. This one. This is the common part, right? So if this is set A or event A and this is the set of event B, then this is the event of A intersection B. So notationally, how do you write this? A, the reverse of union. So A intersection B. So common part of A and B, that is called intersection. Clear? These
Yes,
all
sir.
are not new to you, right?
No, sir.
No, sir.
So okay, then I can be a bit faster then. So now, if you go back and again come to mutually exclusive events now, exclusive outcomes were exclusive events. So earlier we studied mutually exclusive outcomes, which was basically outcomes that cannot occur together. So now mutually exclusive events are also events that cannot occur together. What do we mean when we say that events that cannot occur together? It means that the intersection of the two events, let's say A and B, should be equal to an empty set. What is this? This is phi. It is called an empty set. So there is no intersection. That means there is no common between the set of event A and set of event B. Just for example, when I took this 1, 2, 3 and 1, 3, 5 and 2, 4, 6, none of these were common, right? All these were mutually exclusive because getting an even number and getting an odd number, that cannot happen at the same time when you throw a piece of die, right? So these are called mutually exclusive events. Is that okay? When there is nothing in common, so notationally the intersection should be a null set. Then you have exhaustive events. So events that together make up the entire sample space, that will be exhaustive events. Events that together give you the entire sample space. Now, if there are, let's say, A1, A2 to A5, let's say, then these 5 events, A1 to A5, they are called exhaustive if the union of all these, A3 union A4 and union A5, this should give you the entire sample space. So sample space is generally denoted as S. Okay. If that is the case, then these events are said to be exhaustive events. This is the mathematical condition. Complement now. Complement of an event. So complement is just the opposite. So complement, it's all those outcomes which are not contained in that particular event. So when I say A complement, it's basically all the items that are not taken away from the sample space. Example, A. In our case, A was getting an even number. So even number, the possible outcomes were 2, 4 and 6. The entire sample space was 1, 2, 3, 4, 5, 6. Right? So now, if you look at the outcomes that are contained in A, 2, 4, 6 and these 6 outcomes in the sample space, if I ask you now what is the complement of A, then it will be all those items from the sample space which are not in A. So it's basically 1, 3 and 5. That's how you get the complement. So anything that is left out in the sample space, that is the complement. So if I show you notationally, for example, this is a bigger set of the entire sample space, okay? And somewhere here you have a set of all these outcomes of event A, then what will be A complement? A complement will be everything that is not A and which is inside S. So if I shade it, then this entire area here, this thing, only except this A, everything else is the complement. Okay, you get this point?
Yes.
Except A, everything is the complement. Okay. So notations, there are two more notations for this. Sometimes it's denoted as A bar or also A prime. Okay, these are the notations for complement. Sub-event, just like you have subset, similarly you have a sub-event. So in set theory, what is a subset? Let's say when you say A is a subset of B, then that means everything that is in A is contained in the set B, right? The bigger set B contains all the items from set A. That is when we talk about set theory. Now, here when we talk about events, we just talk about the outcomes. So now, whatever outcome that you have in event A, all the possible outcomes, if they are also contained in the possible outcomes of event B, then we say that A is a sub-event of B. If all outcomes of event A are contained in the outcomes of event B, then A is said to be a sub-event of B. So again, how do you show this? If you have a sample space, again, this is your sample space. Now, if you have a bigger event called B and A is just somewhere here, if this is A, then if you see all these points, this A set will contain some points, but these all points are also inside this set B or inside this possible outcomes of event B, right? So clearly A is a sub-event of event B. That is what sub-event means, and notationally this is it. Next, is this okay? Sub-event. It's similar to the word subset.
Yes, sir.
Then you have partition. Partition of event A. So partition is, what do you mean by partition? If you have an event A and if you partition it, let's say 8 number of times. So partition would be, let's say C1, C2 and so on. If you go up to C8, okay? So these C1, C2 and up to C8, these are called partition of event A. Let's say this was the entire event A ka set. Then these are called partition of event A when there's a condition. Event A, if the union of all these, union of the CIs where I is going from 1 till 8, that should give you the entire outcomes that are contained in A. So diagrammatically, this is how it looks. Or let's say in Venn diagram, this is how it will be shown, and mathematically this is the condition. So all these different events will be called the partition of event A if the union of all these events gives you back the entire bigger event A. So it's like partitioning the different outcomes. How can you partition our event A? The event A that we were working with was 2, 4 and 6, right? Getting even number. So how can you partition this? So this event can further be partitioned as getting an even number less than equal to 2. That can be a new event, right? Getting an even number less than equal to 2. Then getting an even number less than equal to 4. That is another event. So getting an even number less than equal to 2 will mean only 2. Getting an even number less than equal to 4 would mean this, right? And getting an even number less than equal to 6. That will contain all these 3, 2, 4, and 6. And now, if you take the union of these 3 events, so C1 union C2, union of C3, this gives you back the entire set A, right? That means this C1, C2, and C3, they have partitioned the event A. So this is how you can think about it. So this is called partition of event A. No, this example is not exactly fitting. That was also what I was thinking. Sorry. There is one more condition that needs to be there when you call something a partition. So if you see in the diagram, there was nothing common between C1 and C2, right? But here, when I took C1, C2, and C3, just what I removed, if you see C1, C2, and C3, these were not mutually exclusive. Here, there was a common part which is 2. And then here also 2, 4, both of them were common. So no, this is not allowed. When you take a partition, then these events, these sub-events, C1, C2, C3, this have to be mutually exclusive. So there are 2 conditions. So if number 1 this, and then number 2 is the CIs, whatever events that you are taking, they should be mutually exclusive. So in that case, if you want to partition this, simply call it as getting a 2, getting 2 when you throw a die, and then C2 can be getting a 4, C3 is getting a 6. So now clearly this only contains 2, and so on. So 2, 4, and 6. These are all mutually exclusive, and their union will also give you back the entire event and all the outcomes that are contained in event A. Okay, so this is also an important condition that they should be mutually exclusive. The earlier example did not fit. Is this okay? For something to be called a partition, the union should give you the bigger set and they should be mutually exclusive. The different events that constitute the partition, they should be mutually exclusive. Next is an important point. De Morgan's law. What is that? It has 2 parts. So one is in the form of union. So when you have the complement of A in B, then it can be written as A complement intersection B complement. And then another part of it is when you have the intersection, the complement of the intersection of 2 events A and B, then it can be written as A complement union B complement. It's like whenever you open this complement within the brackets, then this union turns into an intersection and intersection turns into an union sign. Is that okay?
Yes, sir.
So that will go on if you have more number of events also. Example, if you talk about the union, then if you have a union of AI where I goes from 1 till n, and then you take the complement of this. Is this okay notationally? What do you understand by this? Like, is it okay?
It means like A1 complement intersection and then like that. Like for like n number of sets.
Yes. It's the complement and then goes up till an complement. Or in other words, I can write it's an intersection of I going from 1 till n AI complements, right?
Yes.
Okay. So the other part of this would be when we take an intersection of I going from 1 to n AI, and then the entire thing, this entire intersection complement, that should give you the union of AI complement. Fine. This is about De Morgan's law, very important. When you also solve questions, it will be important. Okay. Then indicator function. This is in general a very important thing. Whenever, not for this exam or anywhere, indicator function is a common thing that you should know. So notation, be very careful about the notation. So I is just because of this word indicator. Then you have A here. So what does A show? I'll tell you. IA of x. So since it's a function, so it's a function of x. So IAX, it takes a value 1 whenever x belongs to A. And it takes a value 0 whenever x does not belong to. So this is a sign x does not belong to. Belongs to and does not belong to. Okay. What does that mean? So whatever you are writing here in the subscript of the indicator function, so here I wrote A, which means whenever this x that I have here, if this x belongs to A, that means this indicator will tell me yes, that has happened. So yes is shown as a 1. This is sort of to show the fact that yes. Do we have x in A? Yes. Do we have x in A? No. So yes is denoted with a 1 and no is denoted with a 0. So it indicates whether your x is contained in the event A or not. Do you understand the notation and how it functions? And what is the use of it? So it's an indicator, which means you can get to know whether this particular outcome X is there in the event A or not. Yes or no? Not clear?
Yes, sir. Clear, sir.
Yes, sir.
And I'm thinking of an example. So what will be, for our case, when A was 2, 4, 6, then IA 3, what will be the value of this?
0.
And then IA 4?
So if we're considering the whole set A, so 1 होगी.
Yes.
So it does not mean कि like the whole event has to occur. It means just one of the
Yeah,
the sample
this
points.
yes, if this is one of the outcomes that is there in event A.
Okay.
Okay, moving ahead then. So now some operations. These are just like algebraic formulas if you look at them. So A intersection, and then if you have a bracket containing a lot of unions, say union Bn, then how do you do when, let's say, instead of union and intersection, if you had a multiplication here and then an addition here?
It
What
would
do you
be A
do?
into B1 plus A into B2 plus A into B3 and
So
so on.
similarly here you'll do A intersection B1 union A intersection B2 union. Is it similar?
Yes, sir.
A intersection last name, it will be Bn, right? And the other way around also. So what else? Number 2, what are they saying? If B1, this is called the distributive law. Okay. In normal algebra also we used to call it the distributive law. Here also it's the distributive law. Okay. If B1 and Bn are exhaustive events, then for any event A, Let's go to point 3. Point 2, I don't think there is anything important there. Oh, okay. Okay. No, there is some importance of that. I think let's try to understand. Point 2, what are they saying? If in the above, if in point number 1, for now you don't have any condition on B1 to Bn, right? But if I tell you that B1 and up to Bn, all these events, they are mutually exhaustive. Sorry, mutually exclusive and exhaustive. Exhaustive and mutually exclusive. Mutually exclusive. That means there is no common part between any of these events, and they are also exhaustive. That means their union, exhaustive means the union of these events is the sample space. So now if that is the case, if these all events are exhaustive and mutually exclusive, then if you take something of this sort, then B1 union B2 union Bn, which is ultimately A intersection B1, as we have written above, intersection B2, and then a union of A intersection Bn, right? What is special about this? When you impose this extra condition that they are exhaustive and mutually exclusive, these two things, then this thing, A intersection all these, is basically creating a partition. So all these are partition of set A. That's what they are telling you. So A intersection B1, A intersection B2, A intersection Bn, all these different parts, they are basically partitioning the set A. If you want to look at it visually, then this is what they have drawn. Let me also draw it. I think it will be very clear. If this is the entire sample space, let's say, and here you have B1, then you have B2, then you have B3 and B4, let's say. Okay, so this is the range of B1, this is B2, this is B3, and here the last one is B4. Okay, now if you have a set A here, now what did we try to do? We tried to find out the intersection of A with the entire union of these B events, right? A intersection, which means the common part of A and the union. So A and the union, the common part is what? If this is A, this is event A. Between A and the union of everything, the common part is the entire set A. Just that there are different parts to it. So first part is this. What do you call this? This is the A intersection with the part B1, right? Then here, this is the A intersection with part B2. This is A intersection with part B3. And last one is A intersection with part B4, right? And then when you take the union of all these different parts, that will give you the set A. Yes or no? These different parts, when you take the union, you'll get the set A. And you can see that these different parts, they're also mutually exclusive. They cannot occur together, any of these different parts. A intersection B1, that is separate from A intersection B2. Just because B1 and B2, these were mutually exclusive. There was nothing in common. So here also there is nothing in common. So of these four different, or let's say of these n different intersections, there is nothing in common, and together they make the entire set A, right? So that means it's again satisfying this condition that they are together, the union gives you the entire set, and also they are mutually exclusive, right? Both the things, they are satisfied. Hence, we say that whenever this is the case, then these different events here, A intersection B1, A intersection B2, and A intersection Bn, these all give you the partition of event A. I don't know how it will show up in questions, but this is what it means. And like in terms of concept, you should be able to understand what they are saying. Going ahead, this is simple. A union A complement, that should be giving you the sample space.
Yes, sir.
If you remember that A complement here. So if you have this is the entire A complement, and when you take the intersection with the A, that means the shaded area and the unshaded area, that together should give you the sample space S.
Yes, sir.
Okay. That is this condition number 3. Then what else? Condition 4 is basically A intersection the complement of B can also be written as A minus B. What is A minus B? Everything that is in A but not in B. So A minus B, if A minus B in terms of set theory, how do you write this? If you have, let's say, a different set A and then you have a different set B, then A minus B will be everything that is in A but not in B. B में नहीं होना चाहिए. So 1 and 3, you'll have to remove 1 and 3 because 1 and 3 are there in set B. So this A minus B should give you 2 and 4. And this law is also true. If you see via Venn diagram, let's do this. If there is a universal set S, or let's say there is a sample space S, then there are two events A and there is an event B. Then what is A minus B? Diagrammatically, A minus B is this. If you just look at the picture, then everything that is in A but not in B. So we have to remove this part. The intersection part is removed, right? This is the part of A minus B. True?
Yes, sir.
Now, instead of directly calculating A minus B, what if I took this route? A intersection B complement. Let's take that route. I'll remove this shade and this details. So if this is A and this is B, what is B complement? B complement will be everything that is not in B. So this entire thing is B complement. Yes, just except the B part. Now this B complement has to be taken an intersection with set A. So what is the common part between set A and this B complement? So common part is this only, the earlier A minus B that we had shaded. Yes, this is
Yes,
the common
sir.
part. So that means these two are equal. That's how you can look at it diagrammatically. Next, part 5. If A is a sub-event of B that we learned, then what should be A union B? If A is a sub-event, A is smaller and it's contained within B, then A union B will basically give you the bigger set, which is B. And if you take the intersection, then it will be just A, because that is the only common part between A and B. Can you visualize this? Let's try to do that. Where's the sub-event? Here. So if this is a sub-event, then what is A and B? A and B union. Union will mean this entire bigger set B, and then intersection is only A. Do you understand this point?
Yes,
Yes.
sir.
Okay. So that is about this part. Now we enter the next topic called probability. Till now, we were learning about some terminologies in the beginning: events, outcomes, mutually exclusive, etc., etc. So what is probability? Probability basically attaches a particular mathematical number to some event, right? So when I say A is an event of getting an even number, when you throw a dice, okay, then you know that there are 3 possible outcomes that's there in this particular event, and then the entire sample space, you also know that it's 1 to 6. Then if I want you to calculate the probability of this event A, then it should be the number of outcomes that satisfy this event A divided by the number of outcomes that you have in sample space. C upon 6. N is basically counting the number of sample points that you have here. So half is the probability. This is how you calculate probabilities, right?
Yes, sir.
Okay. So this is, what do you call this? This is basically the favorable cases. Favorable. And here this is the all possible cases. If you make it more simple, then in the numerator you just count the number of favorable cases, and then in the denominator you have all the possible cases. Now, for something to be a probability number, so this is a number. So now we have attached some number using this probability to this event A. And when do you call that probability is valid? Whenever. So this probability should be between 0 and 1 strictly. Not strictly, sorry. Strictly between 0 and 1. No. 0 and 1 can also be the values. So it's not strictly in between. So strictly in between basically means when I say this, right? Strictly in between isko bol dete. But this is not. So 0 and 1, they are allowed. Okay. That is the condition that probability needs to satisfy. What else? The probability function must satisfy the following two conditions. One is that the number should be between 0 and 1, and if you have all different events. So if you have, let's say, only two events, A and B, then probability of A plus probability of B should be equal to 1. If A and B, they together, if A union B, let's say, A union B is equal to the sample space. So basically, if you have only two events which make up the entire sample space, then their probability should also add up to 1, which is quite logical, right? If you think about the case where A is an even number and here B is an odd number, so if you take the probabilities of both of them, one will be half and the other one will also be half, so they'll add up to 1. So if you add up the all possible cases, then you should get 1. Just a second, I'll connect my charger. Okay. Now, what is a uniform probability function? So uniform probability function is if in your sample space, if in the sample space all the outcomes, they have the same probability of occurring, then it's called a, so here probability of getting a 1 is how much? 1/6 if you throw a die. Similarly, probability of getting a outcome 2 is also 1/6. 3 ka bhi 1/6. So on up to probability of getting a 6 when you throw a die is also 1/6. So this means there were total how many outcomes? Here 6. And each of them, the probability is 1/6, 1/6, 1/6 for each of them. That means this is a uniform probability function. Uniform just because you are attaching the same probability to each of these different outcomes that you have in the sample space. Okay. This is about uniform probability function. Then you have, so probability of event, I think you can calculate. Next, continuous probability space. They have briefly mentioned something called continuous probability space. For example, now you look at sample space in a discrete form, right? We looked at the sample space as discrete values. Discrete means just some points. So we just took 6 number of points here. Instead of that, if instead you took they are talking here about spinning something and then it points to some point in the circle. Sure. A circle, a complete circle is, so let's say this is 0 degree, and then if you take the entire circle, this is how much? 360 degree, right? In a circle. 360 degree is also called 2 pi. Pi is 180, so 2 pi. So when you spin this particular circle, then let's say there is a hand which can stop anywhere between. So this hand can take any value. Let's say if you measure the degree going in this direction, then this can be anything between 0 to 2 pi. Yes or no?
Yes, sir.
Now, this entire thing is also a probability space because these are all the possible outcomes for this particular event that we are doing. So we are just spinning this wheel, which is a circle essentially, and then you are noting where is the hand stopping. So the hand can stop anywhere in between the 0 degrees and 2 pi degrees. So now this is a continuous probability space because you're not taking some specific points inside this. This is an entire range. So 2 pi is like it's very big, right? 0 say it will start and up to 2 pi. So it can be anything. So there are infinite number of points here. So that is when you talk about a continuous probability space. Now, what kind of probabilities can you calculate when you have such a continuous probability space? An example is if you want to calculate the probability that this pointer ends up between 3 o'clock and 9 o'clock. So this is 3 o'clock, right? And this is 9 o'clock. So if you want to calculate the probability that the pointer will be somewhere in this region between 3 and 9, then what will be the probability? Between 3 and 9, this is the favorable case. So 3 and 9 will be whenever you are between 0 to pi. So 0 to pi,
Yes.
This entire range that is favorable to you is pi, and the entire range was 2 pi. So the probability of being between 3 o'clock and 9 o'clock is half. Okay. So that's the only part that they have mentioned. I'm not sure if we have any question on that, but if there is, you can tackle, I hope. So now, some other rules about probability. Probability of the entire sample space is 1. Probability of the null set is 0. If there is an empty set, of course, the probability would be 0. The entire sample space occurring, the probability is 1. Okay, just a second. I just want to make sure that you understand this. What do you mean when you say P of S? Probability of S.
Sure event. That event will happen. Like the probability that will happen is
it's a sure event. Yes. So because it's not that the entire sample space will occur. It's that when you note that outcome will surely be inside S. That is why this probability is 1. When you carry out that experiment once, there will be only one outcome, but that outcome will surely be in this sample space.
Basically, the probability that the sun will rise tomorrow is 1, right? So that's how.
Yes. Okay. Next, if there are some mutually exclusive events, A1 to AN, then if they are mutually exclusive, then the union probability can also be broken down. So if you have AI union, I going from 1 to n, if you take the probability of this union, it is simply the summation of all these probabilities. So if I just write it in this way, A1 union A2 union AN, then it is simply A1 plus probability of A2 plus dot 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 plus probability of AN. Okay, so if these are mutually exclusive events, that means there is nothing in common. So taking the probability of a union is same as just adding up the different probabilities because there is nothing in common. Later on, we'll also see how do you tackle common. Just now, we'll see. Okay, for some event A, the probability, again, probability of that event also lies between 0 and 1. That is okay. Then if A is a sub-event of B, then probability of A has to be less than or equal to the probability of B. Because B is an event which contains more sample points. So the probability of B, the event B, should be at least as much as the probability of event A, right? Because A is a smaller subset. So whatever will be the probability for A, that should be smaller. Coming to 0.6. So this is also familiar, I think, for you. So do you know this, that A and B can be calculated? Probability of A and B, sorry. Probability of A plus probability of B minus the probability of A intersection B.
Yes.
If they are not mutually exclusive, if they are not disjoint. Okay, one more thing. When you talk about mutually exclusive, it also means disjoint. Disjoint events. That is another terminology we use for the same thing. Okay, so union, if they are not disjoint, then you also need to remove this part. Why? Why do we need to remove this part? Because if you look at when you add these two probabilities, then this particular portion which is common to both, this gets added up twice. But we don't need that, right? Union, when you take the union, you just need to add this once. That's why you just subtract it once, so that it doesn't get added up twice. Do you understand this point? Why do we subtract this probability?
Yes, sir.
Okay.
Yes, sir.
Next, they also mentioned some probability of union of three things together: A union B union C. That may also be helpful. So let me write it down: probability of A, probability of B, probability of C. Then you just subtract all the intersections. The double intersections have to be subtracted. B intersection C minus probability A intersection C, and then at last you just add the triple intersection. Okay, so this is another formula for you. If you remember the set theory from earlier classes, this should be okay. Here also what happens is, while subtracting these things, you end up subtracting this too many times. That's why you need to add it once. How? Think about it. When you had A, B, and C, let me make this small diagram for you. Only think about this common part, okay? This is a common part between all the three, right? Only this part is common. Now, when you take A, then also this comes, right? When you take B, then also this shows up, and then here for C also it comes up. Now, when you subtract A intersection B, suppose this is A, this is B, and this is C, okay? So when you remove this A intersection B, then also this is getting removed. That means this is a -1, right? Yes or no? Do you see what I'm explaining? Why do we add this? So that's what I'm explaining.
Yes.
So when you subtract B intersection C, so B intersection C also this has this part, so it gets subtracted once. And at last, A intersection C, that also contains this shaded part, so that also again gets subtracted. So that means the 3 times that you had added earlier, you have also subtracted it 3 times. That means essentially this part is not getting added up. because you added it 3 times, then you subtracted it 3 times. So that, but we need this when we take the union. On the left side, we have a union. So we need this. So this should show up at least once. That's why we just add it in the end once. Okay, now another point is probability of A complement is 1 minus the probability of A. Next point, probability of A can be thought of as probability of A intersection B plus probability of A intersection B complement. What is this? A intersection B complement. What is this? How else can you write
Probability A minus B.
this? Good. So clearly, if you look at this diagram, then it should be okay. If this is A and if this is B, this part is A minus B and this part is A intersection B. So these two things together, when you add up, that should give you probability of A, right? Next. Exhaustive events. For exhaustive events, the probability of all the exhaustive events, let's say A1 to AN, when you take the union of A1, A2, A3, and union AN, that should give you 1 because these are all exhaustive. Hence, they make the entire sample space. So entire sample space probability is 1. What else? When they talk about a uniform probability distribution, I think it's not important. No, let's forget about it. Sometimes probability is also denoted using these two words, percentage or proportion. This also means probability, okay? While you solve questions, you will understand that these two also represent the same thing. Or in other words, the question may give you some probability values using these terminologies. That's what it means. They can tell you that 40% of the class has opted for, let's say, subject mathematics. That means probability that some student is studying mathematics is 0.4, right? That is what it means here. And the last one here is for any events A1 to AN, the union probability is less than or equal to the summation of all the different probabilities. That is the last one. So probability of a union of different events, AIs, where I goes from 1 to n, that has to be less than or equal to the summation of these different probabilities of I going from 1 to n. What does that mean? When you have a lot of events, AIs, when you take the union and then calculate the probability, just think about it here. A union B union C, you just had 3 events, 3 different events here. You added up 3 things, but you also ended up subtracting 3 more things, right? That means at best what can happen is it can be equal. So the union probability can at best be equal to the summation of the 3 probabilities. Otherwise, for most of the cases, it will be less because you're subtracting something. See, you're subtracting something, right? So this part is the union. This part is the summation that you see here. See, this is the summation of all the probabilities. This is the union. That means, why is this less than or equal to? Because if these are not mutually exclusive, then for sure you will be subtracting some other probabilities. So this will end up being less than or equal to. Is this point okay?
The part in the right, it just means that we're summing all the events, right? The probabilities of
just as you have here, probability of A, B, and C. So this is what this is the sum of all the P of AI. I going from, let's say, 1 to 3. Here there are 3 events.
And the part on the left contains the intersection as well, so that is why, like, we're subtracting some of the part. That is why.
Yes. So that means this will be lesser than adding up all the individual probabilities. I think you got it now. Puneet, आया समझ में?
हाँ sir.
That ends your chapter 1. Chapter 1, you just have 10 questions. So okay, so let me do this. For now, I'll stop here. For you both, I cannot do chapter 2. Took more than what I was expecting. But okay, if you understood it properly, it's nice. I want both of you to also do section 0 and section 1, both. Section 0 and section 1, try to complete all the questions. Okay, if you have any problems, then please let me know in the group. Whatever questions you are not being able to solve. Next class would be on Saturday. I'll let you know the time in the group.